Okay, this is ChemQuest 17, ionization trends. So we have a little bit of information to look at before we get started. And this says separating charges. It says examine figure 1 below, where there are 3 pairs of metal spheres that have different amounts of charge on them. The spheres in diagram C are closer than the others because they have the strongest attraction. So you look at diagram A and it's just a +3, diagram B it's a +4, -4, diagram C is a +7, -7. So that's basically all we have, and then we are asked some critical thinking questions. So number 1, which would be harder to separate? The 2 spheres in diagram A up here, or the 2 spheres in diagram B, and why? So if you look at those two, the 2 spheres, you have to think of these like a magnet. If we had magnets that were closer together, it would be harder to separate them than if they were further apart. So diagram B is our answer. The spheres in diagram B, I'm just going to write the letter B, are our answer. Why? Because the force of attraction is greater due to the higher charge difference. So we'll say because the force of attraction is greater due to the higher charge difference, and that's why the force of attraction is greater. So now we have to draw Bohr diagrams of the following atoms: lithium, nitrogen, and fluorine. Now hopefully you have your periodic table so you'll know how many electrons to put in these different diagrams, because without it you don't know how many to put in there. So let's look at the Bohr diagrams, and lithium has 3 electrons, so I'm going to put my little dot, and hopefully I can do this. You draw your first energy level, you're going to have 2 electrons, and then you draw your second energy level, and you will just have 1, and that's going to be lithium. The next one is nitrogen. You have 7 electrons to distribute, so you've got your nucleus in the middle, 2 electrons in the first energy level, and then you should have 5 left to put in the next one. 1, 2, 3, 4, and 5. And this is nitrogen. And then our next one is fluorine. Have our nucleus. You've got your first energy level with 2, your second energy level, and we will put 7. Oops. 4, 5, 6, and 7. So hopefully your drawings are a little bit better than mine, because it's kind of hard to write with this pen. And let's see. So the third question. For each atom in question, 2. Compare the attraction between the nucleus and the outer level of attractions. Which atom has the strongest attraction between the nucleus and the outer electrons? So you have to look at how many electrons they have, and that will tell you how many protons they have. So fluorine has the strongest attraction because it has a +7. So fluorine, it has the strongest attraction, and it has a +7. From the nucleus that is attracting the outer level. Nitrogen's outer field +5 attraction, and lithium's outer field is a +1 attraction. So fluorine has the strongest attraction with a +7. So number 4, which would be more difficult? If you wanted to remove an outer electron from an atom of fluorine or from an atom of nitrogen. Now you got to think of which ones have the strongest pull. So for similar reasons as question 1, it would take more energy to remove an outer electron from fluorine than from nitrogen. The outer electron from fluorine feels a stronger force of attraction from the nucleus. So number 4, if you wanted to remove an outer electron from an atom of fluorine or nitrogen, it would take more energy to remove an outer electron from an atom of fluorine than from nitrogen. So fluorine would be more difficult. Would it be easier to remove an electron from lithium or nitrogen? And once again, hopefully you're seeing that lithium does not have a strong pull on that electron. It only has a +1, whereas nitrogen has a +5 pulling on those electrons. So lithium would be the better choice in this one as well. So number 5, lithium would be our better choice. So we have a little bit of information here about ionization energy. Ionization energy is the amount of energy it takes to completely remove an electron from an atom. And the first ionization energy is the energy required to remove one electron from an atom's outer energy level. The second ionization energy is the energy needed to move the second electron from the energy level. The second ionization energy is always going to be higher than the first because it's harder to get that electron. Now, with noble gases, because they have 8 electrons in their outer energy level, they are stable, and therefore it takes a lot of energy to remove an electron from a noble gas. So here are some critical thinking questions. Which would have a higher first ionization energy, phosphorus or aluminum? And if you want to draw a Bohr diagram or use your periodic table to help you, you can do that. So let's just talk about this. Which would have a higher first ionization energy, phosphorus or aluminum? And the answer is phosphorus. And that is because it has a higher attraction. It's got an attraction of +5 to its outer electrons, and whereas with aluminum only has a +3. So phosphorus would be the one that has a higher ionization energy. Phosphorus and aluminum are in the same row of the periodic table, so hopefully you're looking at that. Lithium, nitrogen, and fluorine are also in the same row. Using your answers to questions 3, 4, and 6, what do you notice about the ionization energy of elements proceeding from left to right across a row of the periodic table? Does the ionization energy increase or decrease as you go across the period? And this question is what is important. As you move from left to right across a period or row, the ionization energy increases. So the ionization energy increases as we move across a row from left to right on the periodic table. Explain why you think this trend exists. The attraction between the nucleus and the outer level of electrons increases as we go across. For atoms with a stronger attraction from outer electrons, it takes more energy to take those electrons away. And that's kind of hard for me to write all that in this, but you can pause it and re-listen to it. The attraction between the nucleus and the outer level electrons increases. So for atoms with a stronger attraction for the outer electrons, it requires more ionization energy to remove the electron. So number 8 says to draw a Bohr diagram of sodium. Do you expect the first ionization energy to be high or low for sodium? So when we draw sodium, we've got 2 electrons in our first energy level, and then we have 8 electrons in our next one. In the last energy level, we just have 1. So there's only 1 electron here. So this electron is only feeling a +1 draw to the nucleus. So that's not very high. So sodium has a low first ionization level. Do you expect the first ionization energy to be high or low? So we would expect it to be low. The second ionization energy of all elements is higher than the first ionization energy, and we've said that before. So this is just restating that. The second ionization energy of all elements is higher than the first ionization energy, but in sodium the second ionization energy is extra large. So when you looked back at the board drawing, consider the structure of a sodium ion atom and explain why this might be so. Well, if you notice, there was just one electron in sodium's outer shell. It just had one electron way out here. So we could snag that electron pretty easily. But if you notice, the second energy level had 8 electrons. It was a completely full shell. And so it's a lot harder to try and take one of these 8 than it is just to take that one that's floating out there. So it's kind of like a noble gas. It's really difficult to remove the electrons when the shell is full. So number 10, a certain atom in the third period has a third ionization energy that is unusually high. Using the same reason you used for question 9, name this atom. Now this you'd have to be looking at a periodic table so you can see, and the atom is magnesium. Magnesium is in the third period of the periodic table, and it has 2 more electrons than neon, which is a noble gas. After we take those 2 electrons away, the third one is going to be really hard because that shell is full, just like sodium is up here. Okay, so we got a little bit more information, trend and ionization energy in groups. And we look at those diagrams. Diagram D, we've got 2 horseshoe shapes. They're kind of like magnets, I guess, close together. Diagram E, they're further apart. So number 11, would it be easier to separate the magnets in D or E in figure 2? Now hopefully you answer that it'd be easier to separate E. Assume that each magnet is attracted to the other and that the size of attraction is the same. And just think about only the distance. So hopefully you you're able to understand that diagram E would be the one that's easiest for us to separate. Now, how does this distance between the outer level of electrons in the nucleus in phosphorus compare to the distance between the outer level of electrons in the nucleus in nitrogen? So we have to look at our periodic table to see where those 2 elements are, and so we can understand how to answer this question. So hopefully you're looking at a periodic table. Phosphorus is a larger atom. So let's just put down that phosphorus is a larger atom. And so the distance between the nucleus and the outer level of electrons is greater than in nitrogen. So how does the distance between the outer level of electrons and the nucleus in phosphorus compare to the distance between the outer level of electrons and the nucleus in nitrogen? The distance between the nucleus and the outer level electrons is greater in phosphorus than it is in nitrogen. So number 13, based on your answer to question 12, would it be easier to remove an electron from nitrogen or from phosphorus? Well, hopefully you understand that it's going to be easier to remove it from phosphorus. Why? Because the electron is further away from the atom. It's way out there. So it's easier to take it from phosphorus because it's a larger atom than nitrogen. Nitrogen and phosphorus are in the same column, so hopefully you've noticed that. From your answers to question 12 and 13, what happens to the ionization energy as we move down a column? So as we move down a column of the periodic table, the ionization energy decreases, because the atom size increases. So